as a host, you are honored to be obligated to have a presentation here. So I have to come up with something, and that's why I came up with such a long title for my investigation. It's about numerical investigation on material behavior of hardwood Glulam beam columns subjected to combined bending and axial compression. I can make it shorter. This beam columns subjected to combined bending axial compression are columns with the risk of in-plane buckling, for example, or slender beams who have the risk of lateral torsional buckling. And then my research, I wanted to focus here on the material behavior, because hardwood differs a bit from softwood, and I wanted to re-evaluate how this contributes to the current rules of the Eurocode 5. Because in future I plan to do more research on in-plane buckling of glulam made of hardwood, for example beech or oak and something like that. But just to show you where the difference is, when we have, for example, here a normal compression in the direction of the grain, the normal test we know from the EN 408, we have for spruce a low deformation curve, something like that. We have here around 85% from the maximum strength. We reached our elastic range, and then we have a plastic strain complaining here, but it's not really that long. But this kind of low deformation behavior is already included in the well-known formula we know from the Eurocode. But when we go further and look at beech, for example, here glulam 40HA, we have a much bigger deformation. Also here in that case around 85%, we have the proportionality limit, and then we have around double the plastic strain we have, for example, for spruce. This is even stronger when we look, for example, in beech LVL, for most of you known, for example, as Baubuche, where we already have the proportionality limit at 65% from the maximum limit. So why is this important for stability behavior? It's important because we have a reduction of our E modulus. When we look at that, we get our E modulus from this line here. We can from the, how is it called, how it grows, and when we get on the top it gets lower, lower, lower until we have no E modulus, or we lost every stiffness we have in our material. And that's why I wanted to look deeper without any stability in it. How does it affect the load bearing capacity, and how is it even to model? It's easy to model because I wanted to create also easy model, in this case sophistic, so other students, for example, can build up on that in bachelor thesis or master thesis. I wanted to include that also in a script, so it's really automated. And in that case I use some shell elements with a material nonlinear analysis, again without any geometrical effects. I have no imperfections, so we won't have any theory second order moments or loads in that thing here. And I assume isotropic material behavior, because right now in sophistic you can only model nonlinear material behavior with concrete and with steel, but I could like change the concrete that it's representing timber just by using the right characteristic values, or to define it with the right strain stress diagrams. I use in that case also the correct values from beech GL48 from Erhard from his dissertation, and the build-up is also like we know it from the EN 408. We have two loads in the third points here, and then we have axial load here on the side. That's the one I loaded first, and then I continue to grow within the bending loads until I reach the end, or the failure occurs. I wanted to look at two stress-strain relationships, or which are derived directly from the load deformation behavior. One is the bilinear elastic plastic stress-strain behavior, which is the basic one used in timber. This is also one already implemented, for example, in Sophistic. It's easy to use. We only have on the compression side here one line on that side and a other straight line implementing that there is no stiffness anymore when reaching the maximum strength capacity. And on the other side, we have here the tensile strength, which I model as the bending tensile strength, just really easy without any strengthening or something like that. And on the other side, I used a nonlinear elastic plastic. I built it up for myself from the character values I known from Erhard, for example, and then I used the current guidelines or the first guidelines for timber structure, which are based on a new standardization, also from steel, where we now have a bit rules how to deal with finite element design in steel or timber engineering. And then I have a growth to 85% in that case of beech glulam, where I reach my proportionality limit. Then the plastification occurs until I reach the compression strength. This strength is nothing else than this one, but it has a new name because we have to differ between different points in our compression side. And then we have the softening which is occurring, and softening here, which just says, okay, it can't take any more load, but it will keep it steady loaded. I also implemented here, so you can see it. For example, the difference here for spruce and also for beech is around 15%. That's what I meant earlier with the 85% when the proportionality limit is reached. We have around 42% one time for the plastic strain, which is like when we take 42% from the elastic part, we add it on the plastic part here and then again. So we have a really long way to go with our element here. And lastly, I modeled it that way that we always have a tension failure in bending. So my calculation ends when the strain or the stress is reached, because normally we won't have a compression failure. That doesn't really exist because, of course, on the compression side we have always plastic behavior. What occurs when we have a failure, for example, in experimental testing, one side is giving a lot of tension at some point because the plastic line is moving all the time, and then we get high tension, and then we have tension failure and bending. But when we use numerical investigation, we have always to check, is our numerical model really accurate? Is it good? And therefore, in the new guidelines, we have some rules we have to follow. First, we have to do a verification. We want to implement, or we want to look, is our model really modeled right? How is the engineering judgment? Does it make any sense? Because when it doesn't make sense at the beginning, we don't have to do the calculation. So I looked into my my beam column, cut through it, and looked at the failure. How does it look? And it looked really, really good compared to the stress-strain relationship I earlier implemented in my Sophistic model, and I showed you earlier. So that's how it looks right now. And for me, that was enough. It corresponds well with the thing I implemented. So it was good to go with that. And also I have to check the discretization. That means how many elements do I even need in a finite element model. I can just go with 2, for example, or 3. For most of you who are using, for example, finite element in offices, most of the time these elements are already built in from the programs. They just give you a number and they do internal checks. Is it really a good number of elements? But if you're working mostly in scientific field, you have to really look yourself, how does it fit? In that case, I made some calculations for 20 elements of the height, 30, 40, and 100. And when I would have 1 million elements or endless elements, I would get the exact result, which is 850 kilonewton, because at the end I made this whole calculation with an axial load of 850 kilonewton. So that's the goal I need to have, which is good fitting with the regression line. And then it's not really good to implement endless elements, because then my calculation wouldn't be finished until today. So I need to find a good gap between good results and short calculations time, mostly 30 seconds. 10 seconds would be better. And for me, that was the 30 elements, with also fitting the 5% ultimate load difference. It's also a rule in the new Timber guidelines for finite element structures, where it's said if you have a difference of 5%, it's okay, but it's better if you have a difference of 1%. But for calculation reasons and to have more time at home, for example, it's better to go with this 5%. At the end, I could say my FE model was plausible. It gives plausible results and good results, but I didn't do some verification steps, so don't do that in your theses. These are ones I have to do in the future. For example, the convergence study, where I have to show are the results getting a result at the end. Sometimes my model was failing for really high loads. I couldn't find a solution, so that's something to have to look into. And then we can do some sensitivity checks to look how is the influence, for example, of the shear modulus on our load deformation and stuff like that. Then the next step is, of course, we need also some validation. We can just do finite element modeling. We need also to prove these are really representing the reality. And therefore, I need also experimental investigations where I have to check, are these stress distribution in my beam as the same from the reality. So my goal was to calculate the load-bearing capacity. So what can my beam really take? And therefore, I did the numerical calculations, in this case sophistic. Then I did some data processing, take the results, recalculated that in Python, and then I sent it to this analytical formula where I integrated the stress distribution you can see here over the height, and then we get the load-bearing capacity in axial direction and the load-bearing capacity of the moment. And that's how it looks at the end. We have two lines. One is the non-linear elastic plastic material behavior with softening. This is the solid line here, and the dashed line here is the bilinear elastic plastic behavior. And we see for axial loads up to 730 kilonewton, the difference is only 1.5%. So we don't have a big influence in using a nonlinear model or with a bilinear model. But then, after that, we get massive differences, up to 35%, where I wondered, because I thought if I model it that way, these should look really the same, but I got differences where I had to look deeper into that. Also, when I looked into the differences of the axial forces, for example, I see that I have a difference of around 15% here, which, if you paid attention, is similar to the factor for the proportionality limit. It's basically the same, so there must be some influence of that. But first I wanted to check, is the bilinear model really right? And because the bilinear model is really easy to model, also for analytical models, I used an analytical model, in that case from Hursting, but there are some other people, Van der Put, who also have some nice analytical model which are really easy to use. And both of them correspond very well, and the differences between them is the difference I get from the finite element model, where I approximate the solution for the elements. So I guess when I have 1 million elements of the height, both of these models should basically give the same results. Maybe you wonder why I don't use an analytical model after all, also for the nonlinear analysis. This is at the end really hard to implement, because for the bilinear model I just have two straight lines, but when I get a curvature into my analytical model and I want to model at the end the loss of the E modulus, it's hard, because I need to find some way to derive or integrate that stuff, and then I need also some lines which have like a polynomial line form. That's better to use in that case, some finite element modeling I know from experience. And then I looked again, okay, what is the case with the nonlinear elastic plastic material behavior? And then I cut again inside my beam, looked inside of it, and at the beginning I saw, okay, both look really the same. We have the known compression tension side with a little bit of plastic behavior here on the top. And when I get to the point where both of them start to differ from another, I get for the nonlinear elastic plastic this nice also behavior of softening and plastification. And when I go further, I see this behavior. I see a high softening part in my beam and this little plastification part and my tension, which is really hard to find. It's also the reason why it's hard to find solution inside of this area, because the strains are getting really high and my tension part is getting really low. So a little bit more of bending can lead to a huge amount of strain, which means that my finite element model finds it's hard to find really a solution. And that's how it looks at the end. And that doesn't really look right. I get immediately no tension on the side, but I still say, okay, I have tension failure. And my whole beam is under compression, which doesn't make sense, because in that case, we are looking, for example, into the same cases I told you earlier. I look at a pure compression test where I should have a straight compression at the maximum. That's why this doesn't make sense. And the reason behind that could be that this is the modeled failure mode. So this is the load bearing capacity at the failure state. But what is when I have my maximum load bearing capacity before that? What is when I have that before I reach the failure? And that's something I have to look into. My model wasn't really suitable for that yet. It didn't have any matches for that, but in future I want to use a more complex finite element model. So this is also something I achieved. I saw that sophistic or easy finite model program, I would say, or rather easy program, has some problems sometimes with calculating that stuff, and so maybe it's time to switch to other programs, for example to ANSYS or Kratos, some open source finite element modeling. So in conclusion, what I already expected, the bilinear model is easy to implement, and the problem for that is I have no consideration of the softening and plastification on whatsoever. So this model is no choice for me at the end to use when I look into stability behavior, because I need this plastification, I need this proportionality limit, I need all of that to model a real beam column at the end. I can do that with this kind of model, but at the end maybe I don't get the right results, because the load bearing capacity isn't right modeled if I give him the idea that tension failure will occur, or the maximum load bearing capacity is at tensile failure in bending. And the third option I have is to derive load deformation behavior directly from experimental results. Because if you look at that, these are derived from pure compression tests. This behavior is derived completely from bending tests. But what is between those parts? What is when I have axial load and bending? How does this beam really behave? Do we really have this kind of softening, or will it just continue with it? Because in the literature, if you have pure bending, we also have a plastification, a really low plastification, but there are already some points where I can see that we need own low deformation behavior, but that's hard to get on its own, because we can't look inside of a beam, we can't model the stress strain, or we can't get it just from looking from it, because we can only measure deformations. But that's something you can do for me, for example, in a master thesis. So get in touch with me. Thank you so much. Maybe you can work on that together, and if you have questions, I'm happy to answer. Thank you.